Hello there, I'm Hao, and this is just another video of me solving random problems. So let's begin. So today we want to find the k closest point to the origin 0, 0, and we are given an array of points here, where the subarray will be an array of the coordinates on the graph, right? So we can calculate the distance by this equation right here. And let's say we have a rectangle right here. So the hypotenuse is C. The adjacent is A and the opposite is B, right? We can calculate we can calculate C square by using this equation. Root is coming from the pi Pythagorean theorem, right? Where we have a for square rectangle, right? And C can be calculated using the square root here, right? And C will be the distance. And what is A and B? A and B would just be x2 minus x1, right? Same for here, y 2 minus y1, right? Which is x2, x1, and then y2 is here, y1 is here, y2 is here, right? So so x1 and x and y1 we always be the origin, right? Because we want to find the distance uh to the origin, right? So the origin we always be the second point. So this will be always be 0, right? So we can simplify this to 0, right? So this can just be x squared plus y squared. Right, x squared plus y squared, right? Where x and y will be our separator for the coordinates. And then since we are comparing the distance, right? We can just get rid of the square root. We can just square them, right? They are the same thing. So this is our equation here. We can simplify it to this, from this to this, right? Okay, so this is the equation, right? Let's write it down. So this can be calculated by x squared plus y squared. So how do we do this? We can do it in one way to do it is we can sort it, right? We give it a time complexity of O of n log n, right? And the space will be O1, right? So after we sort the coordinates based on in ascending order, right? Let's say the distance is 3, 6, 9, and 12, and k is 3, and we can return the k best result, right? The k closest to the closest point to the origin, right? So that is one way to do it. So let me give it a try and code this up. It's actually pretty straightforward. We can just return points of sort, right? And we have point 1 and point 2, and we want to return the k best result, right? So 0 to k. Okay, and how do we sort? We just find the distance, right? We're just comparing the distance. So p1 of 0, which is x, plus p1 of 1, which is y, squared, minus this will be point 2, right? The index 0 here will be x, and index 1 will be y. Okay, what's wrong here? Oh, I forgot to square this. Of course, a squared plus b squared, remember? Okay, submit. Cool, and it worked. So another way we can do this, we could give us we can optimize for time by given with a trade-off of some space here. So the second way we can do is we can use a max heap. The max heap give us a time of O of n log k, and the space is O of k, right? So the idea is that we will have a heap of size k. So what is k, size k means? Which means that at any point in time, our heap, we always holding the best k result, right? As we iterating to the heap, then let's say we are at index 4 and k is 3, then we guarantee that in the range of that 4 coordinates, the heap will always hold the best 3, right? So that is what the case here meant. And why is the time is n log k? So n means we need to iterate through n elements, right? For the point to n. And then each time we add something to the heap, we need to simplify down. So that is log of k, right? Why not log of n? Log of k because we at any point in time, the heap will be of size k, right? So the depth will be size k, not n. We're not holding n element, we're holding k elements here. So it's log of k. Because k is always less than or equal to n, most of the time the runtime will be better. So let's look at an example here that we can say we have 3, 1, 2, and then 1.5 here. Let's say this is 5, right? And then 1.5 here, right? And let's say k is 3, right? So we can. So I'm not gonna draw the tree here because I don't want to show the heapify and everything. We just assuming that the heap will work, right? The heap will work. So 3, 1, 2, right? So first of all, I will iterate to k to the points array k time. So 1, 2, 3, right? And stop here and add them into the heap, right? After that, uh, we will keep iterating through it and then comparing the point, the distance, comparing the distance at that point to the origin, right? The distance to the origin of this point to the distance to the origin of the point in the heap at the root, right? Because at the root, we will always have the largest distance. We always have the point with the largest distance from the origin, right? So this will be our worst distance in the whole heap, right? So we want to compare to that. So if we have even a worse distance here is even larger, then we ignore it, right? However, if we see a smaller distance, right, then we want to extract the map, delete that, and add our next best uh, distance or point into our maxif. And at the end, we can just return the heap data. So that is the general idea. So let me code this up. So I'm not gonna spend time and build out the whole heap here. I'm just gonna use a heap that I already have, and I assume that we are familiar with the heap, how the heap works here. So a few things I want to point out is the distance here. Usually the heap we just holding integers, right? But now we are holding the point array, right? So whenever we want to compare something, when we heapify up or down, we want to use the distance function here to calculate the distance from the point to compare. And we also have the max distance function, which will always return the max distance at the root, right? Which is the biggest distance from the origin, which is at the root of the heap, right? So we can create a max heap here. So max heap equal to new max heap. Right, we can, and now we want to add k element to the heap, right? Before we compare 11k and I plus plus here. Okay, and we want to do max heap push, right? The points at I. Okay, so what do we do next? The next thing that we want to do is we want to keep iterating to the remaining elements in the heap, right? So here we have we start at less than k, so now we start from k, right? And we start at point of length and I plus plus, and we want to calculate our current the current distance from the point, right? Because we want to compare the distance of the at the current point to the distance the worst distance in the heap, right? The largest distance from the heap. So this is point of I, and then we can do the current disk. is equal to x squared plus y squared. Y squared. And then if the current this is, so if it is larger, right? And we will just ignore because we want k best result, right? Our heap we always be holding the k best result as we iterate. So if it is larger, we will ignore. But if it is less than, we will so max heap dot max difference. If it is less than, right, we want to update our max heap. We want to get rid of the worst distance, which is the 4, and then add the next best distance. Right? So max heap push points of I, right? And at the end, we can return the max heap of data. So let's give it a try. If you're using Python or Java or any language that have like a built-in heap, go ahead and just use that. There's not the heap. There's no built-in heap in JavaScript. So that's why I have to be one. But general, like this is the general solution. It's not gonna be like this long if you already have a built-in heap. So this solution is pretty good, right? But there's actually another way we can do it. So we can do this using a min heap as well. The time would be O of n plus k log of n. And the display would be constant. So what does the O of n here mean? So the general idea is that if we're gonna have a heap of size n, not of size k, but size n. So we're gonna use the point array to build out the whole heap, right? The min heap, right? So because it is a min heap and it have n elements, and we want the k best element, right? The k best element means the k smallest element because we want the distance that is closer to the origin, right? So we want the minimum value. So after we finish building the min heap, we can just extract the minimum from the root k times to get the best result, right? Um, so look at an example here. So we have 3, 2, 1, 4, 5, whatever. So we're gonna build our heap, right? So let's say this is our heaps, right? That, and remember, I'm putting a distance here, not the point, just to simplify the example, right? So let's say the n is 5, sorry, the k is 3, right? So after we finish building the heap, we can just like pop 3 times, right, from the root. So this is 1. The root always have the smallest value, so 1, right? And we hop 2, right? Hop again, 3, and we can just return this, right? We have to store the result, right, to return, but I think it's still O1 because actually okay, but because we have to actually if we are thinking of it in that way, then it should be okay of space for every single solution. Like for the sort, right? We have to slide it from 0 to k and then return it. We're combining it in one step, but we can also like have to store it in an array and return it. But you get the idea. So the thing I want to point out here to focus on here is the space complexity. So the reason that this might be better is because if n is super large, right, then n plus something will always be better than n multiplied by something, right? So if n is large and k is small, right, then this will be worse and this will be better, right? Because k's will be most of the time will be smaller than n. Okay, so let's try this out. So I'm just gonna delete our example here. Hello? Okay, sorry, technical issues. So let me get rid of the max heap here. We don't need that anymore. So what can we do? We can, okay, and also I forgot to mention the reason that it is O of n is because we can build the heap is O of n. So usually, right, we have to iterate to n elements, and we need to every time we add something, we need to heapify down or heapify up, right? So that is log of n. So we need to do it for n times, so n log n. But we can use the Floyd algorithm to do it in O of n. Please look it up if you're not familiar with it. So the general idea is that we can skip half of the uh, node because half of the node could be the leaf node, right? Is at the last level, right? So we can just skip that. So look this up, you will find something like this. It's because we can just keep half of the elements in an array, right? You just keep half of it because those elements at the leaf is already valid because they don't have any element. They don't have any children below them, right? Because like we need to keep the invariant of the heap, right? So if it is a min heap, then we have to make sure that the parent is smaller than the children, right? If it is a min heap, because the leaf node don't have any children, so they are already valid because we don't have anything to compare to. So the idea is that we can just get rid of half of them, right? Like if we look at the second to the last level, they might be valid, they might be not. But if they don't, then the maximum level that we have to traverse is one, right? So just traverse down by comparing and swapping with the smaller element, right? So like this, and then and divided four. So the next level will be two step, and the next level will be three step, so on and so forth. You got the idea. So that is why it is O of n, and the k log n. What is the k log n? So remember at the end when we finish building the heap, we need to pop k time from the root, right? Um, so because we have to do it k times, so that is k multiplied by log of n. Because every time we pop, then we need to swap, right? And then heapify up, right? Because our heap is size of n, it's not size of k anymore, so then it's log n. Okay, so we can view our heap here. Um, so we can start from the second to last level, right? We can find the parent index by looking at the master floor, right? Voice length minus one divided by two. And we want to do it in place, right? For constant state. So let's see. We're looking at the parents, right? So we're starting from the parent, the second to last level, right? So this is actually already so if we look at, okay, if you look at the parent of the last element, what does it mean? If you look at the children, if you look at the parent of the last element, which means you are on the second level, right? The second to last level, right? And we can just iterating from there. So I equal to parent, right? I greater than or equal to zero, and then I minus minus, and we can heapify that, right? Because the poise here will be our heap now. We can do it in without doing it in place to save the space. So we can do heapify down, passing in the index of file. And we can create a function for that. So function heapify down, function index. So we can calculate, we can do the left index equal to start, right? And y left index is equal to start. This is just to get into the while loop for the first time. Or the poise at the left index It's not unified, right? We want to keep unified. So left index is equal to what? To um, left index is equal to I multiplied by 2 plus 1, right? Which is the current index multiplied by 2 plus 1, right? The right index is similar. Right index is plus 2. And then we want the minimum, right? The min index is equal to left index. And we can say if we have the right index, so let's say if we don't, if the left index is greater than or equal to the quotient value, we just return, right? And then if um, the right index is less than or equal, less than quotient length, right? And the points at the right index, the distance, the distance at the right index is less than the distance at the points or at the left index. Right? In that case, we want to set the mean to the right index. Right. So we are just choosing we are just choosing the smaller index here, the mean index here. Why do we need to do that? Because if the current node is invalid, then we want to swap it with the children, right? With the smaller children, because the in the mean heap, the parent always had to be smaller than the children, right? So that's why we have to pick the minimum um distance here before in case we need to swap. And of course we need a distance function, a distance, just taking a point, and we can just return point zero multiplied by point zero just like before, plus point one multiplied by point one. Okay. And yeah, and then we can check if the current the current point is valid, right? So if uh current index, if the distance at the point of the current index is larger than the distance at the point of the mean index, right? We want to swap it, right? The points at current index and then the points at the mean index is equal to points plus the mean index and then the points at current index. We want to swap it, right? And we want to keep simplify. So we set the current index to the mean index, right? The mean index, remember the mean index is index of the minimum index of the children, right? So we set the current index to the children. So we just keep simplifying that until we are in the valid spot. Like if it is valid, then we just go ahead and return, right? And then after we fill out our heap, we want to pop it take time, right? So let's have the result array here. We can return the result at the end, return result, and then we need to do it k time, right? So I less than k, I plus plus, and we want to do result that push uh uh poll, right? Let's create another method called poll. We will polling the root element. So what do we want to do? We want to set the mean, right? The mean point, the minimum point. So the mean point is always at the root, right? The parent at the root. So index zero. So we always at zero, right? And we can return that at the end. mean points. And then what do we want to do? We want to remove it, right? So how do we remove it? We swap it with the last one, with the last element. So this no, so point of 0 is equal to points dot pop, right? And then we want to hippify that. Hippify that at index 0. Okay, so that's pretty much it. Give it a try. Okay, what did I do wrong here? So I start. Okay, we set the minimum. Like we start at the left and we set to the right that the right is smaller. Distance equation is correct. If distance, the point, current index. What is the current index? Okay, here. Yep, is greater than the distance, the mean index. Then we want to swap them. All right, makes sense. And we reset the current index to the mean index. Okay, that's right. Let I equals to parent minus minus. The result. What do we do here? I equal to 0, I less than k. Result of push pull, right, which is the element at the root here. Force dot pop, if I dial 0. Yeah, that's still correct. So why do we get 1 and 3 here? Interesting. Okay, I figured out that I have like an extra parenthesis here. So let's try again. And it worked. Submit. Okay, accepted. So thank you for watching. We can optimizing for time using different approaches here. There's trade-off between space and time, and also the complexity of the implementation as well, right? So again, thank you for